Hello, this is Mr. Stansbury. I'm going to take you through the notes on graphing polynomial functions. At the end of this, you should be able to say, I can use the degree of a polynomial to determine the shape and other characteristics of its graph, and I can describe the characteristics of a parent function. Okay, so I know this is super overwhelming, this big, huge chart and all, but I think it's going to make pretty good sense when we're all done. Okay, so here are four different graphs. This is y equals x to the first, y equals x squared, y equals x to the third, y equals x to the fourth. Okay, so these are four different graphs, and we're going to look at all these different characteristics for each graph. But what we're going to do is we're going to probably just go through and look at each graph and figure out the domain for all of them. So domain, if you remember, that's what the x's can be, right? The x's. So what can the x's be on this? Goes forever and ever to the left, forever and ever to the right. So that would be all real numbers, which is the r with the extra little line through it, right? And if you look at these other three graphs, forever and ever to the left and to the right, forever to the left, forever to the right, forever to the left, forever to the right, all of these are going to be all real numbers. Okay? Now, the range is what the y's can be. Now, if this here, you'll notice it goes down forever and it goes up forever. So the range on this is also going to be all real numbers. But if you'll notice on x squared, it starts at 0 and only goes up forever and ever, right? So our range here is going to be a little different. So this one, the range is going to be, starts at 0 and actually includes 0. So we should make a square bracket, 0 to infinity. Okay, now if you look at x cubed, it goes forever and ever down, forever and ever and up. So this is also all real numbers. And then if you look at x to the fourth, if you look, it comes down and it kind of makes this little wiggle down here and goes back up. So it's going to be the same as the x squared, 0 to infinity. Okay, all right. Okay, end behavior. So that's what happens to it when it gets forever and ever big and forever and ever small. Okay, so let's start off writing with all of these. So if you'll remember we got to write it like this. As x goes to negative infinity, y goes to what? As x goes to positive infinity, y goes to what? So as x goes towards infinity, y is going towards positive infinity. And as x goes towards negative infinity, y is going towards negative infinity. Okay, on this one here, as x is going to infinity, it's going to infinity, and same thing, as x goes to negative infinity, it's still going to positive infinity. So these are going to both be positive infinities, and really these two are acting the same. So as x goes to infinity, y goes to infinity. As x goes to negative infinity, y goes to negative infinity. So what x goes to negative infinity, it is, oops, did I mess this up? I did these backwards, sorry. Negative infinity, positive infinity, as x goes to negative infinity. Yep, so x goes to negative infinity, y goes to negative infinity. As y goes to positive infinity, sorry, as x goes to positive infinity, y goes to infinity. Okay, and on this one, as x goes to negative infinity, y goes to infinity, and as x goes to positive infinity, y still goes to infinity. So these are both infinity. Okay, the zeros, where does it cross? Where do these things cross the x-axis? So remember, zeros is x-intercept, right? So look, 0 there at 0, 0, right there at 0, 0, 0, 0, and 0, 0. So all of these x-intercepts are at x equals 0. Okay. Increasing intervals. So when is this thing increasing and when is it decreasing? So if you look, as we're going left to right, this thing is always increasing. Okay. So what we're going to want to do there is say from negative infinity to infinity, it's increasing. Okay. Now this one here, increasing intervals, this is only increasing once it gets down to 0. Now it starts increasing. So that means I would do this. I would do 0 to infinity. So from 0 to infinity, it's increasing, right? And on this one, as you're moving left to right, it's always increasing. So from negative infinity to positive infinity, it's increasing. And then on this one, it's only from when it gets past 0, it starts increasing. So that's from 0 to infinity. Okay? Decreasing intervals. This one here is never decreasing. So there are none. Okay? On this one here, it's decreasing from negative infinity to 0, right? So negative infinity to 0. This one, it's never decreasing, so none. And this one, it's decreasing when it goes up to 0. So from negative infinity, oops, that's hard to read, sorry. Negative infinity to 0. Okay? Positive and negative intervals. So basically, when is this thing up above 0? Okay? So what we want to look at here is when is this thing above 0? It's above 0. It's a positive interval when it's greater than 0. So 0 to infinity. This one is always positive. It's at 0, 0 here, but just think of that as from negative infinity to infinity. It never goes into the negative portion of the graph. Okay, this one here is positive from 0 and above, so 0 to infinity. And then this one, same thing as the one above it. It is always positive, negative infinity to infinity. Okay, negative intervals. This one's negative when it's from negative infinity up to 0, right? Negative infinity to 0. And then this one is it doesn't have any negative intervals. Everything's positive, so none. Right? And then this one here is negative from negative infinity up to 0. And this one's always in the positive, so this also has none. Okay? And then even or odd functions. Now, what we want to do with this is basically it's an even function if it reflects about the origin, about the middle here. So if we reflect this over, we get this here, so that is not even. So that would make it odd. This one, here's our vertex right there, and it does reflect over that line, so that's even. And same thing here, this does not reflect over this line here, so that's odd. And this does reflect over the origin line there. The axis of symmetry, it has one, so that is even. Now I know you can also look at the powers and say, oh, first is odd, second is even. It does get a little tricky when it's written out in different forms, and it can be hard to tell, but yeah, that's even and odd functions. Okay? Okay, we're going to take a look at a couple examples, but first let's take a quick little comedy break.
Time in my life where I see a walker without the tennis balls on the bottom. Honestly, all the technology we have nowadays, could we please slow down production on the next iPhone and just dedicate a couple guys from Apple to work on the tennis ball, on the walker problem we have running rampant in this country?
All right. So let's take a look here. Example 2. Consider the function g of x equals negative 1/2 x minus 3 to the 4th power plus 1. What is the parent function? Oops. Right there. Oops. No, that's not what I want. Sorry, you don't want to see that again. Right there is our 4th power. I want blue, that turquoise. There we go. So that our parent function is going to be, say, f of x equals x to the 4th, right? Okay, or y equals x to the 4th. Identify the parameters of g of x, and so as long as it's in this form, then this is what we'll end up getting here. So our a here that's a negative 1 out there, right? So a is negative 1. B is whatever's in front here, so that's our 1/2. And then x minus h, so it's minus 3 here, or what do you put in for this? What do you put in for x? So this equals 0 is going to be 3, and then what's at the end? A positive 1. Okay? And then now create a table of values and sketch the graph of g of x. So let's fill out this little formula here, our little mapping formula here, and then we should be in good shape, right? So if we got x divided by b, if b is 1/2, so this is really x over 1 over 2, that's really just the same thing as 2x, right? So instead of writing that, we're going to write 2x and then plus the h plus 3 is part of it. And then a is -1, so we do -1 times y, or just -y. And then we're going to add k, which is +1. All right, so here's our formula. So we just write 2x plus 3 and -y plus 1. So parent points of x to the 4th. So let's do, let's come up with some pretty easy ones here. So let's do, we know that it's even, so we know it's going to be like, basically looks like kind of a U with a kind of a flat bottom almost there. So let's do 0, and let's do 1, and then let's do 2. Okay? All right. So if we plug in 0 for our parent point, 0 to the 4th power is going to just be 0. If we plug in 1 to the 4th power, that's still 1. Oops, so we got 0, 0, we got 1, 1, and we do 2 to the 4th power is 16. So that's going to be 2 and 16, like that. Okay? Now, we put over here, we put symmetric points. Since it is even, it's going to have a symmetric point. Okay? So the point of symmetry here for 0, 0 is just going to be the vertex, right? Which is 0, 0, right? And then this will come in handy actually after we actually have our new point. So let's leave that alone for now. But 2x plus 3. So we're going to simply plug in. For this here, we've got 2 times 0. In fact, let's not even put the parentheses in there so it doesn't look as confusing. 2 times, I always put in whatever I plug in parentheses just so we know that we're plugging something in. 2, 0 plus 3. Okay, and then we're going to do negative y, which is 0, plus 1. So that there is going to then give us 2 times 0 is 0, plus 3 is 3. And negative 0 is 0, plus 1 is 1. So there's our first point, okay? And then we'll fill out the symmetric point here in a second because it'll make more sense once we have some of these all figured out. Okay, so then now we're going to do the same thing here. We're going to do 2 times 1, so that's our x, plus 3, and then negative 1 for the y. Not y, but negative 1. And it's positive 1 plus 1, which will then give us 2 plus 3 is 5, and negative 1 plus 1 is 0. Okay, and then last one here, 2 times 2 plus 3, and then negative 16 plus 1, because again, we're just plugging in the x for the x and the y value for the y here, and that's going to give us 2 times 2 is 4 plus 3 is 7. And negative 16 plus 1 is negative 15. All right? Okay, let's plot these 3 points here. So we're at 3 and 1, right? And then we are at 5 and 0. And then we are at 7 and negative 15, which is right there. Okay, so we got part of our graph looks like that. Ooh, except for that's a horrible line. Let me fix it. Okay, that's about as good as I could get. Sorry. So now our symmetric point on the regular original graph, it's 0, 0, but not on this graph because our vertex is going to be this point right here, right? Which is at 3, 1. So that means that this is not going to reflect because it's already at the vertex point here. So then what we'll want to have is we're going to want to have like ourselves a little, just so you kind of get a better idea, a little axis of symmetry, right? Because all of these points here are going to reflect straight across. So what we're trying to get at here is that this point here is going to reflect straight across this line right here. So if it's at 5, 0, that's a distance of 2 across. So we go 2 back this way. So that's going to be back here. Instead of going through and calculating it all, we know it's going to reflect straight across. So that's going to be at 1, 0, right? And this point down here is a distance of 1, 2, 3, 4 away. So we're going to go 1, 2, 3, 4 more over. And that's at -1, -15 is the other point. And then we can sketch that. I'm going to not make you watch me have to try to sketch this. That's pretty close. Okay? Okay, we're going to do one more example. I know we're already kind of running long on this video. We'll do one more quick example here, and then we'll do the second half on a different video. Okay? Consider this function here. What's the parent function? Y equals x cubed, right? Because there's our cube, and there's no other extra powers in there. Let's find all our parameters. A is whatever's in front. That's 1/4. B is whatever's in front of the x, and that's a 1 there. So that's 1. H, what do we plug in for x so that we get 0? -1. And then K is -2. Okay? So using this formula here, we're going to do, our new point is going to be x over b. So that's just x over, officially that's x over 1, which is just x, right? So we'll just do x. And then we're going to add the h, which is -1. So we'll do x minus 1. And then for the b, we're going to take the a, which is 1/4. So we're going to take 1/4 of the y. And then we're going to add the k, which is -2. Okay, and then now, how to choose points on this here. Since this one is not an even one, it doesn't reflect, we're going to actually want to do points on both sides. So let's do, say, -2, -1, 0, 1, and 2. Okay, so then what we'll do here is we'll just go through and calculate what each one of the original one is. -2 cubed, so -2 times -2 times -2 is -8. -1 cubed is -1. 0 cubed is 0. 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. So here's all of our parent function points. Okay, and then now we're going to go through and calculate all these here. Okay, so we're going to plug in -2 for x. So we do -2 minus 2, right? And then we're going to do 1/4 of 8, -8. And then minus 2, which gives us -2 and -2 is -4. And then 1/4 of -8 is -2, and another -2 is -4. Okay? Or this is supposed to be -1, not -2. So that's going to change all these. I apologize. So that's minus, so -2 and -1 is -3. Oops. Oh, not this one. This one still stayed the same. Sorry. It was just this one. Okay, so we get -3, -4. I'm just going to pause this and go through and do the math for you so you don't have to watch all that because this is going to turn into a 20-minute video already. So, okay, so here's all the rest of the math all done out here. And so then now we'll just go through and graph all these points. -3, -4. Right, I'm going to pause and graph all these points too so you don't have to watch all that. Okay, so here's what our graphed points look like. So we're just going to have to kind of sketch through and roughly figure out what it looks like. So it's going to go something like this, and then it's going to go up like so. Okay? Okay. That's all we have for the first half of graphing polynomial functions. I promise the second half will not be almost 20 minutes long. So if you have any further questions, please feel free to ask in class. Thanks.